Approximation, a polynomial function approximation as another polynomial function. A black box function fx approximation as another polynomial function gx. So if I have a function fx, if I have a function fx and fx is a polynomial function or fx is a black box function, I don't know. What is fx? I don't know. If it is like that, then can I do the approximation, estimation of fx as polynomial function gx? If I have a function fx, if I have a function fx and I have a function gx, what is gx equivalent to fx? Gx is replica of fx, but the way gx is defined is different. Fx is polynomial, multi-level polynomial, or fx is single-level polynomial, or fx is combination of polynomial, non-polynomial. Fx may be a black box. In any case, if I have fx, then what is equivalent of fx? That is gx. Gx is exact. If this is gx, then gx is exact copy of fx. Gx is exact copy of fx. Now gx is a separate function. Fx is a separate function. Fx is input. Gx is output. So what is input? Fx can be a singular polynomial function like t to the power 4 or t to the power 2, a function that is t to the power 2, 10 t to the power 2. If that is the case, then how I can reproduce this fx as gx as if it is k into t to the power 4, again k into t to the power 4, but the input what I receive from fx is not k, not t to the power. If k t to the power 2, then not k, not t to the power 2. Information I get from fx is differentiable derivative. That is the idea. If fx is a function, from fx I calculate the various derivatives, and that derivatives I feed to another gx, and gx is able to replicate fx. That is the concept. This is what we saw. So if fx is k is constant. If ft is kt square, then if I do dual derivative, then it will become 2k, just 2k. If I say that dft by d2ft by dt square is 2k, just 2k, then this is what I can give it to you. Now ft, ft is kt square, then gt, what it would be? If d2 ft by dt square is 2k, it said, well, very nice. So if that is the condition, then what I can do is that d2f d2f by dt square into t square divided by factorial of 2. So if it is 2k, then 2k into t square by factorial of 2. So kt square, it could reproduce. If here it is kt to the power 3, then if I do triple differentiation, power 3 means triple differentiation, so that it would come as a scalar. Then 6k. If I get 6k as triple differentiation from ft to gt, then it would become, at that moment, it would become d3f by dt cube into t to the power 3 divided by factorial 3. So 6k t to the power 3 divided by factorial 3. So it will come as k t to the power 3. So any polynomial equation of singular power, one power, in ft can be reproduced in gt, where gt is d to the power n ft by d tn t to the power n divided by factorial of n. If ft is mixture of all the polynomials, okay, t plus t square plus t to the power 4 plus t to the power 11 plus t to the power n. Plus can be negative somewhere and there are coefficients. There can be constant also, that is interception on the y-axis, y0. Okay, then here also I will add all the component in GT. We saw for 2, we saw for 3. From single, we'll keep adding now. So it is now dft by dt t plus d2ft by dt square into t square by factorial 2 plus d3ft into t to the power 3 by factorial of 3. Keep doing this. So t to the power nft dt power n, and then t to the power n divided by factorial of n. So equivalent of ft in gt, full term, full you have to add, because there it would be added full, here also added full. There if maximum is 10, the maximum you have to do till 10 only, n is 10, because beyond that it will be 0. Now ft is a black box. Ft is a black box, then can we do the reproduction? Can I reproduce it in GT? Yes. Then you have to get the df by dt, d2f by dt square, df3 by dtq, like that till dnft by d to the power dt power n. Get all the all the derivatives constructed. So for any ft, I can reproduce as gt. So approximation of any function can be done in gt, and that is take work dy by dt. Now, if now we use this concept, now if ft is passing, ft is a, we consider ft that passes through a function that passes through origin. If this is the origin, then ft passes through origin. Then it satisfies x0, y0 as 0, 0. But if it is passing through a point that is 0, y0, x is 0 and y is y0, means this whatever the curve we had, we shifted the curve up along y0. If y0 we shifted along x-axis, then that point is 0, y0. If that is the case, then equation would be y equal to ft, y equal to ft, means y equal to all the expression. Now y minus y0, all the expression. So it will become y0, I can take that side, and it would become ft equal to y0. Y0 is nothing but f0. When x is 0, what is f? That is y0. So ft is nothing but y0 plus whatever it is. Now if I come to gt, then gt also becomes f0 plus whatever it is, dy by dt, dy by dt into t plus d2y by dt square into t square by factorial 2, and so on. If it is passing through a point that is x0, y0, x0, y0, then ft is nothing but ft equal to y0, that is f at x0, y0, y0 is nothing but the vertical where the independent component, the dependent component vertical, where the independent component x is x0, then it becomes f x0 plus all the points in ft plus whatever was in ft. So, or fx. So rather you can say fx. So fx equal to yf at x0 plus whatever. Now wherever x is there, I have to replace x with x minus x0, because now it is shifted, whatever the curve we had is shifted x0 along x-axis and y0 along y-axis. So curve, if this is the curve and it is passing through origin, curve I shifted here, where this is x0 and this is y. So that is now ft, I have to replace fx, I have to replace with fx0 plus full fx, and wherever x is there, x minus x. Here in gx, when we are writing gx, that is polynomial equivalent of fx, then f at x0 plus f at x0 plus, and then whatever nice thing we are doing. So dy by dx what we are doing, and d2y by dx square what we are doing. We address with dy by dt. Now consider t is x. So dy by dx. So dy by dx, what we are doing, so that is okay. And now x would be replaced everywhere with x minus x0. So if it is x square, now it is x minus x0 whole square. If it is x minus x to the power 3, then it is x minus x0 to the power 3. Now we kind of extended to finding if there is an extreme point. Extreme point means first derivative is 0, and extreme point lies at x0 y0, where x is x0 and then equivalent there is y0. So at point x0 y0 there is extreme point. Then at extreme point it is maxima or minima. This is what we try to calculate anyway. Now fx at x0 y0 will have same equation, fx0. No, I'm sorry, gx. We had fx, and fx dfx by dx, where there is an extreme point, it is 0. Extreme point is at x0 y0. I have a curve. I have a curve line, and curve line has extreme point, means maximum or minimum. Along x-axis this is x0, and along y-axis that is y0. So at point x0 y0 the curve is extreme point. Now this is fx curve. If I get gx, that is polynomial approximation of fx, then gx equation is f at x0 plus dy by dx x minus x0 divided by 1 plus d2y by dx square x minus x0 whole square divided by 2 plus d3y by dx cube into x minus x0 to the power 3 divided by factorial of 3, and so on. Now dy by dx is if I want to find the maxima or minima, then dy by dx that is calculated, it is calculated at x0. d2y by dx square is calculated at x0. So those are scalar now. d3y by dx cube is calculated at x0. Those are scalar now. So dy by dx is 0. So it is fx0 plus d2y by dx square into x minus x0 whole square by factorial 2, because first one gone. dy by dx gone because that is 0. And plus so on. This is what we saw. Equivalent of fx gx fxy gxy in multinomial, in multivariable case, that also we saw. Okay, so multivariable case, now if we see, then fxy, earlier it was fx, one independent component along x-axis, then one dependent component along y-axis. Whatever I am drawing, each x has a y, and if I connect all y, then it becomes a line or curve. But in 2 dimensions, in 3 dimensions, the number of independent components are 2, x and y. This is xy plane. Each point on xy plane is x comma y. Against each x comma y, I have a vertical, that is z, x-axis, y-axis, z-axis. Each point on xy plane, x comma y, has a vertical component, that is z. So this point is x, y, z. If I have so many z points in vertical component, if I connect all the z points, it becomes a surface. If xy is in surface, xy plane, then z constitute a surface. So 3D, we have a surface. If I connect all the surface, probably it becomes a sphere, paraboloid, cone, whatever. This is what we have already seen. If that is the case, then polynomial equation, polynomial equivalent, polynomial expression gxy for any black box fxy, the way it was in 2D. Now 3D it is same. I have to get partial derivatives if fxy is a function and it has all the degree of polynomial, degree 1, degree 2, degree 3, degree 4, full x, y, x square, y square, x to the power 3, y to the power 3, x to the power 11, y to the power 11, if everything is there full, okay, then here also for each we have to create full. For if it is only one, so consider that it is power 2. If it is power 2, then I have to calculate 2 power 2 double derivative, partial derivative. Partial derivative is nothing but if I have a surface equation and I make a cut in xz plane, there is a cross section in xz plane, there is a cross section in yz plane of the 3D shape what we are seeing. If I make a cut and then I get a 2D plane, in this 2D plane, whatever the surface equation I have, now if I do the differentiation, that is called partial derivative. If this is z and this is x, dz by dx in this plane means per unit change if I see along x-axis at any point x, if there is one unit change around x, how many unit change I see along the z, dz by dx, delta z by delta x at any point x. At any point x, if x is different, then dz by dx would vary, as dz by dz by dx may be function over x. If it is constant, then it is constant. Okay, so partial derivative in xz plane along x-axis, partial derivative in yz plane along y-axis. So dz by dx and dz by dy we calculate. So if I have a polynomial fxy is a polynomial function of power 2 ones. If that is the case, then we calculate do double order partial derivative. d2z by dx square, d2z by dy square, dz by dy. So d of dy, d by dy of dz by dx. Okay, first I calculate dz by dx. Whatever value I get, I again differentiate it with dy. So if I call the d2z by dx square as f and at the kind of underline or down xx double derivative f xx means d2z by dx square. Then if fxy is polynomial of degree 2, then fxx is nothing but the fxx is nothing but d2z by dx square. So we are calculating fxx, fxx, fyy, and fxy. So if three component from fx function, now function is fxy, f in bracket x comma y. If function is fxy and I am calculating f down xx, fyy, and fxy, if these three components I give it for approximation, then I can have another function gxy that is fxx into x square divided by factorial of 2 into fxy into xy divided by factorial of 1 factorial of 1 plus fyy into y square divided by factorial of 2. So now if it makes intersection at any point, that is x0, y0, z0, where z0 is nothing but f x0, y0, then I can have gxy as f x0, y0 plus, because the formula of the surface what we are seeing, that will be z minus z0 equal to, and then full. So z minus z0 I can take out that side and it becomes z equal to z0 plus whatever. Z0 is nothing but fx0 y0. So gxy equal to fx0 y0 plus fxx x minus x0 whole square by factorial 2 plus fxy into x minus x0 y minus y0 in braces by factorial of 1 into factorial of 1 plus fyy into y minus y0 whole square by factorial of 2. So we saw that this is exact approximation of fx in gx as far as second order polynomial is concerned. If fx has 3, 4 equivalently, we can have gx. Now fx is full first, second, third, or fourth order. Then gx also we can make it full. So first order fx, if I have, that is first order fx, if I have, that is x to the power and y to the power 1, then there are two partial derivative that is possible is dz by dx and dz by dy. From that, if I try to get gxy, then that is dz by dx, that is fx into x plus fx into y, fx into x plus fy into y. Now, if I calculate gx in all polynomial terms, then it will become fx x plus fyy. Intersection x0 y0 is 0 0. It is passing through origin. Consider this. So then it is passing through origin means x0 y0 z is also 0. It is passing through origin. So fx0 y0 is 0. So now the equation is fx into x plus fy into y plus fxx into x square by factorial 2 plus fxy into xy by factorial of 1 into factorial of 1 plus fyy into y square by factorial of 2 plus, now if we go for x to the power 3 component, then it will become fxx into x to the power 3 by factorial 3 plus 3 fxx fy x square into y by factorial of 2 into factorial of 1 plus fxyy into xy square divided by factorial of 2 into factorial of 1 plus fyy into x y to the power 3 divided by factorial of 3 plus so on. Okay, so we proved that by differentiation we can get differentiation formula where we have partial derivative. If I have a fxy as polynomial and it is of power of only one type, yeah, either power of 1, power of 2, power of 3, or power of n, then I can have gxy as approximation of fy, and I can reproduce fx exactly as gx. Gx is exactly a replica of fx. If I, the partial derivative, I multiply with xy or xy or x square y, whatever, divided by some factorial. If fx is combination of power of all the polynomials, then gx similarly I can make power of all the polynomials. So this we have in detail, these we have seen in the previous kind of sessions, videos that you can watch. Now, idea is through differentiation, we can prove that if it is two-dimensional or three-dimensional, it is two-dimensional or three-dimensional. If I get the derivatives from fx can be polynomial of 1 degree, fx can be mixture of full polynomial, or fx can be black box. In whatever case, if I extract the derivatives, then I can reproduce with the gx. This is what we saw. And we proved it through differentiation that we took the degree of 1, degree of 2, degree of 3, and through the derivative, if I wrote the gx, it is exactly like that. This is what we have seen in fx and fxy, both places. So in fxy, we took the plane as x plus y. If it is x, if it is x, if x, it is fx in two-dimensional. If independent variable is x, then dependent variable is fx or y. In three-dimensional, if independent variable is x plus y, then dependent variable is fxy, that is z. So here we took x as x-axis, there we took xy plus y as xy plane. We will see more on it. Anyway, now the concept is x I replace with x plus y as far as 3D is 3D is concerned. Now the concept is, can I, if I proved it through differentiation, if I take differentiation, then exactly I can reproduce it. Can I prove this, the polynomial expression as polynomial expression, whatever we, polynomial approximation of fxy as gxy, can I prove it through integration? Integration by part. Integration by part. What is integration by part? if I have two functions fx gx, if I have two functions that is multiplied fx into gx, and then I have to do integration, so fx into gx dx integration. This is integration by part. If I have fx and gx, if I have to do differentiation, then I'll do differentiation by chain rule. Fx d of gx by dx, fx d of gx by dx plus gx d of dfx by dx. So first, if I have two multiplication term fx and gx, and I have to calculate the derivative, fx I'll keep outside and I'll differentiate gx plus gx I'll keep outside and I would differentiate fx. This is chain rule in differentiation. Now, as far as this is now integration, if I have fx and gx and then I have to integrate with dx integration, then instead of chain rule we call it integration by part. So fx I have to keep and then I have to integrate only gx, gx dx integration. Fx I have to keep outside and integrate only gx. Whereas in differentiation, fx I have to keep out and we have to differentiate gx. Here I have to keep fx out and I have to differentiate gx. I have to integrate gx. This is integration by part. Minus, there it was plus, here it is minus. Minus, then do the integration. Integration of what? Integration of two terms. First term is differentiation of fx and second term is integration of gx. So differentiate fx dfx by dx and then integrate fx dx. Differentiation and integration. Whatever it comes, integrate it again as a whole with the dx. So if you have fx into gx and if I have to do the integration, fx f braces x, f braces x into g braces x dx integration, fx gx integration, that is equivalent to fx you have to keep outside and integrate the gx minus then integrate of two terms and dx. First term is differentiation of fx and second term is integration of gx. Whatever comes whole, you have to again integrate with dx. So this is integration by part. Okay. Now I have a function called fx. Now fx is a function and it is a black box. From this function, what I can get is derivatives. First order derivative, that is f dash x, that is dfx by dx. Second order derivative f dash dash x by dx square. F2 df2x by dx square. F3 f triple dash x by dx cube. So these are the derivatives that we get from the fx. Now, if we go more on it, then fx equal to what? Fx equal to integration. I place an integration sign x0 to x. The limit of the integration is x0 to x. Fx equal to integration of x0 limit to x. Now inside the integration we place f dash x dfx by dx into dx. Same thing, right? Now if I say integration of dfx by dx with dx, then it results in fx1. Now if limit is x0 to x, then it is fx minus fx0. Or I can say fx equal to fx at x, fx fx equal to fx0, fx equal to fx0 plus fx minus fx0. I believe it is all right. So fx equal to fx0 plus fx minus fx0. So fx0 and fx0 minus, they will cut each other. So fx equal to fx0 plus fx minus fx0. Now that is equivalent to fx0 plus. Now fx minus fx0 would become integration of something from limit x0 to x and integration of f dash x with dx. F dash x is nothing but dfx by dx. So if I differentiate fx, then it becomes f single quote x. So dfx by dx is the differentiation of fx. So dfx by dx, if I integrate it with dx, this is nothing but fx1. And now, if I have limit from x0 to x, then it becomes fx minus fx0. So fx equal to fx0 plus fx minus fx0. Fx minus fx0 is nothing but integration of limit x0 to x of f dash x dx. Okay, now can we proceed now? So fx0 is the first term, that we leave it as it is. Next term is integration from x0 to x of fx f dash x dx. Now there are two terms if you see clearly. One is f dash x, that is dfx by dx. Another term is multiplied by 1. 1 is missing here. So we talked about fx dx integration by part. Now here fx is f dash x and gx is 1. And then I have to do integration with dx and then from x0 to x. So f dash x I'll keep out.